So a warm welcome to everybody, particularly a warm welcome to this afternoon's speaker, Irit Dinur. So you will see her in a minute online. Let me also welcome Kurt Mehlhorn, who gave a beautiful introduction to the subject in the morning, because we are celebrating something like 20 plus epsilon years of P versus NP. And this afternoon's talk will also be devoted to that. And so I'm happy that you're here. Subsequently, we will also then have the celebration part of this semester or of the past years, which couldn't take place because of the reason you know, possibly. I don't have to spell it out. And I think now I hand over to Martin, who will then introduce more closely to you our speaker of the afternoon. Thank you, Martin.
Thank you very much, Jörg, for the general introduction to this afternoon. So indeed, this takes place in the frame of this more general day on 20 plus years of Millennium problems. That's what we are celebrating all over Germany in a series of events that take place at different places. So yesterday there has been an event in Bonn, and previously there was one in Münster, and there will be others in the next weeks and months. And we in Berlin, we decided to do P versus NP, so to remind us all of this important mathematical question, one of the 7 Millennium problems. And so in the morning we had this nice event in the Futurium, in particular for high school students and so on, where Kurt indeed gave a beautiful lecture. And now in the afternoon we gather here to celebrate this among, let's say, colleagues, mathematicians, and so that's the frame today. Now it's my great pleasure to introduce Irit Dinur. When we planned this entire day and we thought about what would be nice topics for lectures in the afternoon for you, for this audience, then we thought, well, one of the most exciting developments that is tied also to Irit's name is the development of the PCP theorem, which can be seen must be seen in the context of P versus NP as well, of course. So, and I'm very happy that Irit accepted to give this lecture today here for us. Unfortunately, as you realize, she cannot join, but this happens these days, unfortunately. But we very much hope, Irit, that we can welcome you here in person, maybe next year or sometime in the future. So that would be great. Now let me introduce Irit shortly. Irit is a mathematician by education. She obtained her PhD in 2002 from the School of Computer Science at Tel Aviv University with Shmuel Safra. And afterwards, she spent time at various locations, in particular in the US. She was for some years at the Institute of Advanced Studies in Princeton. She spent time at NEC Research. She was at UC Berkeley in California as a Miller Fellow. And afterwards, she joined the Weizmann Institute, where she is still today, as a distinguished professor. Irit's research interests are broadly in the area of foundations of computer science and combinatorics, so somewhere at the borderline between mathematics, theoretical computer science. In particular, she has done brilliant work in the area of complexity theory. I mentioned the probabilistically checkable proofs that are tied to her name because she came up with a new, very elegant, short combinatorial proof for the PCP theorem. And so that's tied to the area of hardness of approximation, where she has worked. And recently, she has also been active in the area of high-dimensional expanders. I cannot read the entire list of awards that Irit got, but let me just mention a short selection. So she won an ERC prize. She has been a plenary speaker at ICM, at the International Congress of Mathematicians, in 2010. She won the Erdős Prize in 2012. In 2019, she was awarded the Gödel Prize for her new proof of the PCP theorem. And only very recently she obtained with others the Paris Kanellakis Award for fundamental contributions to the development of differential privacy. So that's just a short selection of awards she got. We are very happy to have you here today, Irit, at least virtually, and we are now very much looking forward to your lecture, so the stage is yours.
Pardon me. Thank you so much for the two kind introductions. I'm very honored, and also honored to be selected to speak as part of this series on the Millennium questions. And I really, really wish I was there. I had every intention to come, but I tested positive for COVID this week, and I last minute had to cancel. So I hope the virtual format will be still okay. Now, am I sharing? I'm sharing the screen, right? You can see my, okay, good. All right, so let me then start. So I'm gonna talk about P versus NP and about probabilistically checkable proofs. This is the acronym PCP today. Okay, so to start, I want to talk about the field that these topics belong to, and this is the field of computational complexity. So what is this area? I view it as an area that belongs to both mathematics and computer science, and it is the study of intrinsic complexity of computational problems. And the focus is on abstraction and on generality. So we don't care what exact kind of computer you're using or what exact problem you are looking at. We care about the more inherent nature of the computation and how easy or hard it is. So let's look at an example, which I often like to start with. And this is, you're given two integers, two numbers, 43 and 28. What's going to be easier for you, to multiply them together or to add them together? Most people in an audience will say that it's much easier to add them. That's how I feel as well. And I can also back it up with a reason. If you look at the operations I need to do in order to add 28 to 43, you can kind of divide it up into basic operations, which allow me to say add or multiply a single digit. And then, depending on the length of the numbers, to add two numbers, I need to perform how many basic operations, roughly linear in the length of the numbers. If I look at multiplying two numbers, this complexity becomes bigger, because if I want to multiply 28 and 43, I need to first multiply 8 by 43, so I need to go over all the digits of the top number, and then I move to the second digit of the bottom number, 2, and I multiply it through, and then I add everything up. So in all, I get a quadratic complexity. Of course, that doesn't mean that multiplication has quadratic complexity, because it could be that there is a better algorithm. This is the algorithm that we teach our children in grade school, but maybe there is a better algorithm. In fact, the story is that the first time that this question was actually asked rigorously, it was by Kolmogorov in the 60s, and he conjectured that this is the best you can do, and maybe a few days later, a student of his showed a much, much faster algorithm. So in fact, the complexity of multiplication is much more close to addition than you would think a priori. Anyway, this is just an example to show what is computational complexity. It's really trying to understand the number of atomic steps that you need to do, but you don't want an answer which is like a number. What you want is an answer which tells you the relationship between the length of the input, n, and the complexity. So here, for addition, it's n. For multiplication, maybe it's more like n log n. And in fact, it's still open to this day. What is the exact complexity of this algorithmic question? Okay, so now let's move to P and NP. I understand that there was a lovely talk earlier, which I missed. But anyway, P and NP are classes of problems where you kind of bunch together many different computational problems based on their difficulty. Okay, so P and NP are kind of a rough bunching together into the most, to me, interesting complexity classes. So P is the class of problems that have efficient, what we call polynomial time algorithms. And when we say polynomial time, we mean exactly that the relationship between the length of the input and the time it takes to compute is polynomial, like n or n squared. So examples include multiplying two integers. Another example is if you're given a set of linear equations over many variables, find a solution. That's easy to solve by Gaussian elimination. Another example is finding the shortest path in a graph. You know, Google Maps and Waze do it all the time. I'm here, I want to get there, what's the shortest path? These are things we know how to compute. NP is a broader class of problems, so we believe. And these problems, maybe we don't know how to solve them, but at the very least, if someone gives me a solution, proves to me that some system of equations is satisfiable, I can check it. So NP is the class of problems that you can efficiently verify a solution if you are given one. And examples are, for example, factoring an integer. So we just said that if we have two numbers, it's easy for us to multiply them. But if someone gives me a big number and he says it came as a result of multiplying two numbers, we don't know an efficient algorithm to break this into the prime factors. Of course, it's easy to check. If you give me the prime factors, it's easy for me to multiply and see if I got the number, the initial input. So that's one example of a problem in NP. Another example is coloring a graph. You need to color the vertices so that every edge sees two different colors. That's easy to check. If you are given a coloring, it's easy to check that it's okay, but it's very hard to come up with the coloring on your own. So sometimes these solutions that are easy to check, we call them proofs, NP proofs, because they prove to you that, you know, that the graph is colorable, or they prove to you that a given three-sat formula is satisfiable. So the assignment to the variables is like a proof of satisfiability. So we say solution or proof interchangeably in this area. So here's a quiz where I often give a kind of a popular crowd. What does the letters NP stand for? So the first answer, which is wrong, is not P. The second answer, which is correct, is non-deterministically polynomial time. Non-deterministically means someone is guessing non-deterministically the proof, and the polynomial time verifier checks it. But I think that kind of colloquially, really what you should think about when you think about NP is these are problems that maybe you need a proof, but if you have a proof, you can check it. So that's a good way to think about NP. Unlike P, where you can actually compute, for NP, you need a proof sometimes. Okay, so conceptually, one good way to think about NP is that you can go over all possible solutions, say all possible colorings of a graph, all possible solutions to a system of equations. And whenever you find another possible solution, you can check if it's correct. And if not, you move to the next one. So you can always solve these things by exhaustive search because you have this extra verification procedure. And there is some feeling, which we don't yet know how to justify with the mathematical rigor, that this is the nature of NP-hard problems. They really need exhaustive search. You can only improve so much about exhaustive search. Whereas problems in P, you can compute much, much, much faster. And for me, I'll tell you, when I first learned about this, I was in my last year of undergrad, and I took both pure math and computer science. I really loved both of them, and I love the fact that math is so beautiful, and at the same time it can express things from the real world, like physical problem. But when I learned complexity, and I learned that this question, the difference between P and NP, which felt to me like such a philosophical question, understanding the difference between something you can think through and figure out, as opposed to something that you need like a eureka moment, some idea, and then you can check that your idea is okay. These feel like very, very different things, and the fact that you can rigorously, mathematically formulate the difference between these two things, this is the P versus NP question, I just found it amazing that mathematics can capture not only physical phenomena, but also something deep inside our own thinking. So, of course, this drew me to this area, and I went to the instructor at the end of the semester, and I said, I really want to work on this topic. Can you advise something? And he suggested then Muli Safra was supposed to come as a new faculty, and he told me, this guy is working on something related, maybe go talk to him. So I'll get to that in a minute, but first let me tell you what kind of research today is being done related to the P versus NP question. Okay, so, as a student, you kind of hope that maybe one day you will be able to make some progress towards proving that P is not equal to NP. Today, I'm already not that optimistic, and I don't believe it will be really solved in my lifetime. And this was even before it was announced as one of the Millennium Problems, but it was clear that it's a very, very deep and hard problem. So why is it so hard? So to prove that P is not equal to NP, you need to show that there is some language. We just use this term language. You can think of just a computational problem like 3SAT. You need to show that there is some L that on one hand it's in NP. That's usually easy to show. But on the other hand, you need to show that it's not inside the class P. And showing that something is not in the class P, you need to show that every algorithm that is in polynomial time cannot solve this L. That's very difficult to do, because how can you capture all possible algorithms? And this is the notorious subject of computational complexity lower bounds. How do you prove that some class of algorithms cannot solve a problem? And we are struggling very hard to prove better and better lower bounds. The way, and there's a lot of research in this area. I put here on this slide excerpt from Simon's Institute at Berkeley. It's an institute for the theory of computing. We had an entire semester dedicated to lower bounds in computational complexity. And if you see the picture, you'll see that there is this person, very struggling and pushing a huge rock up a hill, this Sisyphic kind of work. This is supposed to represent the fact that proving lower bounds is very, very difficult. So to give some sense of what people do these days, what they do is they focus on various ways to restrict the class P, to focus on maybe a smaller class of efficient algorithms and try to prove that for this smaller class, they cannot compute some problem. And even these restrictions are often very, very difficult. And here's an example of something that looks easy, but actually it's a very important open question. If you look at a random function on n variables, a random Boolean function, so there's 2 to the n inputs, and you select a random function means that for every input you select a 0 or 1 at random. Now, just by counting how many different computational circuits there are, you can immediately see that the size of a circuit that will compute a random function must be very big, much bigger than polynomial. So it's easy to show via counting. But show me one specific hard function that you can prove for it that there is no polynomial time circuit. This is an open question. Okay, so this problem is quite challenging. Okay, so this was about computational complexity lower bounds. Now, another direction where you can study the P versus NP question is through trying to understand better just the class NP in itself. You can also try to understand the class P, and this is all about algorithms. But for me, somehow I was more kind of captivated by this NP thing. And so I met Muli Safra, who was a new faculty, and he introduced me to probabilistically checkable proofs. So what is this thing? The origins come from interactive proofs. People with motivations from cryptography and also complexity started thinking about what other resources you can add to a conventional classical proof. For example, in cryptography, it's natural to think about like two parties or maybe more, and they interact. I want to prove something to Bob, and Bob asks me questions, and I give answers. So there is interaction. And also there is randomness. Randomness turns out to be crucial for cryptography. And various models were suggested, and suddenly people realized that with this extra randomness, for example, many powerful things emerge. And that's the origins of the PCP theorem that was proven more than 30 years ago. And really, essentially, what does this theorem say? It says NP has proofs. So remember, proofs are these solutions for the problem that are both easy to check, so they're local. Every checking step is very small and local, but also robust. So you don't need to go through all the checks. It's enough to go through some of the checks. I'll say it a bit more rigorously in a minute. So the way we like to say it is that if you're trying to prove something to me, you can tell me your proof, but then I will have to read every single step in your proof, because if there's a bug, it might be hidden somewhere, and if I don't go through the entire sequence, I might miss it. But there is another way to compile your proof into a PCP proof, and in that format, I don't need to read the whole thing. I can just randomly read a couple of steps, and I know with high probability whether the proof is correct or not. So that sounds a bit impossible, but okay, we'll talk about it some more. So here's a cartoon I like to put from Madhusudan. You think of the mathematicians' problems that, you're a professor, you're very busy, and someone sends you for referee this huge manuscript that says the Riemann hypothesis, I've proved the Riemann hypothesis, and the guy's name is Errors Happen, so you're already suspicious, and the number of pages to follow is like 15,000, and you really don't have the energy to read the entire thing. So really what you should do is ask this guy, why don't you send me instead the PCP version, the PCP proof? And then I will check it very quickly and see. So of course, this is just a cartoon. Don't really take this too seriously. Okay, so I want to now say a couple of words, a couple of slides on what the PCP theorem is, slightly more mathematically rigorous, in a slightly more mathematically rigorous way. Okay, so I'm starting with a three-set formula. A three-set formula is, if you remember, you have a bunch of Boolean variables, x1 to xn, and you have many clauses. Each clause is of the form x or y or z or not z. So each clause is very small, looks at only 3 bits. And the three-set problem is there an assignment to the variables that satisfies every single one of the clauses? Okay, so three-set is a celebrated NP-hard problem. So if I prove the PCP theorem for it, it's okay. By reductions, it applies to everything else. Okay, so what does the PCP theorem say? It says, if I start with a three-set formula phi, there is a polynomial time algorithm. This is the PCP algorithm that converts the formula phi to a new one, psi. And psi has two properties. The first is, if the original formula was satisfiable, there was some satisfying assignment for it, then psi is also satisfiable. Psi might have more variables, different set of variables, but it has this property that if phi is satisfiable, then psi is satisfiable. And moreover, if phi is unsatisfiable, if no matter what assignment you assign the variable of phi, you will always get some clause to be unhappy, to be unsatisfied, then for psi, it's much, much worse. Every assignment to the variables of psi will violate many, many, many of the clauses in psi. Okay, maybe like 10% of the clauses in psi. Okay, so that's the content of the PCP theorem. And why is this exactly the same as what we said before? So let me try to explain it. Once I have this polynomial time algorithm that converts from phi to psi, notice that this is a polynomial time algorithm. It looks at phi and it creates psi. Because it's polynomial time itself, it does not know if phi is in the satisfiable case or in the unsatisfiable case. Nevertheless, the algorithm has this property that it's a correct reduction. So it generates psi with the properties that are mentioned above here. So now, if I want a proof that phi is satisfiable, and I want a proof that is a PCP proof, one that you can check very quickly, what I will do as a verifier, a polynomial time verifier, I will compute psi and ask the prover not to give me an assignment for phi. I will ask the prover to give me an assignment for psi. Okay, I'll get an assignment for psi, and in psi I know that either all of the clauses are satisfied or at least 10% are not satisfied. So I will check maybe 100 of them, and then with high probability I can tell the difference. Okay, so I don't need to read the entire assignment. I only need to read 100 bits. Okay, so that's quite amazing. It shows you that after you have this transformation, to verify that a proof is correct, you only need to read a constant number of bits. Of course, if you want higher success probability, you should increase this constant. That's all. Moreover, another way to understand the PCP theorem is through the lens of hardness of approximation. So roughly at the same time that the theorem was proven, it was also discovered that this theorem that comes from interactive proofs and has nothing to do with optimization actually has very, very powerful implications for hardness of approximation. Why? What's going on here? Okay, it's the, sorry about that. The reason is that we said that the PCP theorem is really an algorithm for converting phi into psi, right? And it means that there cannot be a polynomial time algorithm that approximates the fraction of clauses that are satisfied. So we know already that 3-SAT is an NP-hard problem. It means that there will be no, if P is different from NP, there will be no algorithm that decides, that given a formula, decides if it's satisfiable or not. But one could potentially hope maybe there is an approximation algorithm. Maybe it is always the case that you can satisfy 99% of the clauses. A priori, that could be the case. The PCP theorem shows that it's not the case. The PCP theorem says if you had such an algorithm, if you apply it to psi, you can distinguish between the first case and the second case, because in the way I set it up, in the second case, psi violates, every assignment to psi violates at least 10% of the clauses. So if you manage to satisfy 99% of the clauses, I know you're in the first case. So maybe I didn't explain it as eloquently as I could have, but the upshot of this is that the PCP theorem is not only a theorem about ultra-fast checking of proofs, it's also a theorem about hardness of approximation of 3-SAT. And just like we talked about 3-SAT, many different problems, vertex cover, maximum click, linear equations, a lot of other problems are proven hard to approximate through this connection. Okay, so we saw that the PCP theorem has some implication towards hardness of approximation. But let's check exactly how much. So suppose I'm given a 3-SAT formula phi, and I ask how many clauses can you satisfy? Oh, I see I have some animation problem. So here is my picture of a 3-SAT formula. You see I have these clauses, x1 or x2 or not x3. That's one clause, and then there's another one, and so on. And now I'm asking you to find an algorithm that will satisfy as many clauses as possible. Maybe there is no way to satisfy everything, but you need to satisfy as many as possible. What's the best you can do? Okay, that's a valid question. And here is something silly that I can do. I can select an assignment at random. For every variable, x1, x2, and so on independently, I'll flip a bit 0 or 1. What's the probability that I satisfy the first clause? Well, x1 or x2 or not x3, there's 8 different 3-bit strings, and only one of them is going to unsatisfy this clause. So I have probability 7/8 to satisfy the first clause. So a random assignment in expectation will satisfy 7/8 of this 3-SAT clause. Of course, notice if this was 4-SAT or some other thing, the number 7/8 would have to change. Nevertheless, we know through much more work beyond just the initial PCP theorem that, in fact, any algorithm that does slightly better than 7/8 will show that P equals NP. So assuming we believe that P is different from NP, you can never do above 7/8 plus epsilon. And of course, you can now ask the same question for every problem, max cut, coloring, click, and so on. So let's look at a specific example because I want to state this beautiful theorem of Hastad, which gave the 7/8 result for 3-sat, but maybe it's even more striking for mathematicians to see the result for linear equations. What's simpler than a system of linear equations over Boolean variables? So these variables, think of them as over GF2. They just take 0 or 1. You have a bunch of linear equations. Each equation only has 3 variables, very, very simple. And you are asked to solve this system. So really, we define the value of the system to be the maximum over all possible assignments to the variables of the fraction of equations that are satisfied. Okay? If this value is 1, if there is a way to solve all the equations, then it's in polynomial time to find such a solution, right? Because you just do Gaussian elimination, you invert the matrix, and you find a solution. So that's very easy. But what if there is the system is overdetermined? There is no solution. Whenever you plug in a solution, it satisfies some of the equations, it violates some other of the equations. Turns out that when the value is 1 minus epsilon, say 0.999, meaning every assignment satisfies less than 0.999, even if there is an assignment that satisfies this many equations, it will be NP hard to find it. Okay? So, suppose you're given a system and you are promised that there is an assignment that satisfies 0.999 fraction of the equations. Can you find an assignment that satisfies slightly less, 98%, 95%, 90%? So Hastad's theorem says that if you're given such a system of equations with 3 variables in each, which makes it easier because these are very simple equations, it's NP hard to decide between 2 cases. First is the value is above 0.99, and the second, the value is below 0.51. So it's NP hard to decide if the system is nearly satisfiable or really completely rubbish. Okay, I find this an amazing theorem. It means that really the random assignment, which will satisfy half of the equations, trivially, is really the best you can do. So it shows that this problem is not only NP hard to compute, it's really NP hard in the most robust way possible. Okay, and this Hastad's theorem also proved the same for 3-sat and for many other problems. And this kind of was the opening shot for a huge amount of work on tight hardness of approximation, proving for different problems exactly how hard is the approximation and finding this number that exactly meets the best known algorithm. Okay, so as I said, the PCP theorem has had a huge impact on this area of approximation and hardness of approximation, and it's been a very active field for the past 3 decades. There are many, many results and connections to beautiful mathematics, geometry, embeddings, analysis, Fourier analysis, probability, combinatorics, and really developed this whole area of discrete Fourier analysis. So it's been a very very active area. And kind of the centerpiece of this whole study is the so-called unique gains conjecture of Subhash-Kot from 20 years ago. And this says that a certain problem called the unique gains problem is NP hard. And if you believe this conjecture that this problem is hard, it immediately implies a very large amount of tight hardness of approximation results. And as for the hardness of this conjecture, there has been some progress on it. Kot, Minzer, and Safra, and also together with me and Kinder, we managed to maybe prove it halfway. I don't know what to say exactly, but we know some hardness about the unique games. And the beautiful thing is that if the unique games conjecture is true, then actually there is one algorithm. It's a semi-definite programming algorithm, which is really the best algorithm for all of these problems that are what we call constraint satisfaction problems, CSPs. So if the unique games conjecture is true, there is one algorithm that kind of immediately is the best for all of these approximation problems. And I want to also connect this to our discussion about lower bounds. Remember that I said, because we don't know how to prove lower bounds for general problems in P, for general algorithms, we sometimes restrict our attention. So for example, you can try to prove lower bounds for these kind of semi-definite program algorithms, and part of this area is to prove lower bounds for these algorithms. We have a lot of success in this direction. Okay, so now let's move to talk a little bit more about what's going on currently on the research on the PCPs. I want to tell you about some stuff that I've been involved in more recently. The PCP theorem is a theorem that we like to call local to global. I know that many areas in mathematics have this local to global phenomenon. I guess it's a natural thing. The local to global here is that an NP proof, which you think of it as something global, right? The correctness of a proof is global. But somehow the PCP allows you to check this huge proof by looking at very small local pieces. You read only a constant number of bits, so that's a local part. And kind of the local, if the local pieces are happy, it means that the entire proof is a good proof. So this is a feature that belongs to the PCP theorem and to the way we construct PCPs. An important component in this thing is what we call a locally testable code. So really, the PCP algorithm, which converts one preset formula to another, it encodes this formula. And so it's natural to do this using error correcting codes, but these error correcting codes need to have this local to global phenomena. They need to be locally testable. And so I will discuss in the next slide what exactly is a locally testable code. But these were kind of formulated during the conception of PCPs. So a locally testable code is an error correcting code that has a probabilistic checker, something that looks at a small part and says if your string that you're looking at belongs to the code or does not belong to the code. Okay, so from now on until for the rest of the talk, I want to talk about these locally testable codes because we have some recent work on them that I'm kind of very excited about, and I thought I will share it with you. Okay, so we're moving to talk about error correcting codes and locally testable error correcting codes. So what is this? An error correcting code, for us, it will just be a subspace, a linear subspace in 0, 1 to the n. So it's a collection of strings, n-bit strings. And what you want from this code is two things. Firstly, you want distance. You want every 2 points in the subspace to be far in Hamming distance. The reason is that you think of this code as being like a dictionary for messages that you want to transmit. And so if you transmit one of the points in the subspace, the adversary that corrupts and makes noise on your message needs to corrupt a lot to confuse with another code word. So that's the distance. What is the rate? The rate just counts how many points are in your subspace, and you want this to be as many as possible so that you can have as many code words as possible inside your code to have efficient communication. So this is error correcting codes. What is a locally testable code? So here in this picture, you see the code. These are the code words, are these dots in brown, and there is some dot that is close to a brown point, and this is the received word. So suppose you get a string, an n-bit string, and you are told, you know, it's in the code, but some errors happen, so it's not actually in the code. It's a little bit far away. And you need to check if it's close to the code or not close. Maybe you need to find the closest code word. Okay, so the basic question is this: given some string, is it in the code? Okay, so maybe it's analogous to our discussion of PCPs, where you're given an assignment to a three-sat formula, and you need to check, is it a satisfiable assignment or not? Okay, but just like in PCP that you didn't want to go through, read the entire thing and check, you want to do it very quickly with a constant number of checks. Also here, you want local testability. You want to decide this by reading a tiny part of this n-bit string. Okay, so a locally testable code with Q queries is a code that has this randomized tester. This is like the verifier in the PCP that looks at the word W, reads only Q bits, and decides if to say yes or no. And it has this property that if W is in the code, you always say yes. And if W is not in the code, you say, I want to say you always say no. But that's impossible because you had an n-bit string. Suppose it was in the code, and then you flip just one bit. Now it's not in the code. The local tester, since it's only looking at a tiny part of your word, it's not going to tell the difference. So the only fair thing to request is that the probability that the tester says no is proportional to how many bits were changed, to the distance of W from the code. Okay. Okay, in Q, the number of bits that the tester reads is called the locality, and codes that have such a thing are called locally testable codes. I want to also tell you a different measure of distance, and this is a different way to define locally testable code. So suppose you have a code like before, and suppose it is defined by a bunch of parity checks, a bunch of linear constraints. I call them T1 up to Tm, so they define my subspace. I can define, given a string, an n-bit string, I can define two measures to how far W is from the code. The first is the most natural, it's the Hamming distance. It just says, take W, what's the smallest number of bits you need to flip in order to put W inside the code? That's the distance of W from the code. The second is the T distance, and that's counting how many of the constraints are unhappy. Okay, that's much easier to compute. If I give you a point and I ask you how close it is to a specific subspace, there's no clear polynomial time algorithm for doing it. You really need to go over the ball around W, and it has exponentially many words, maybe. It's not easy to calculate, but the T distance is very easy. You just go over the linear constraints and check each one, and you can see how many are satisfied or not. And you can even estimate by just selecting a few random of these tests and checking if they're happy or not. Okay, so the Hamming distance is natural, but the T distance is easy. But they have nothing to do with each other in general. A priori, for a random code, for a random linear subspace, if the T distance is small, it doesn't mean anything about the Hamming distance. However, a code is a locally testable code if and only if these two measures are good approximations of each other. So that's very powerful. Now, in order to estimate the distance of a word from a code, we can just randomly sample a few of the TIs. And that's exactly the tester that we do. Okay, so kind of putting us back in context, you know, Shannon invented the information theory, and he came up with these error correcting codes. He looked at random codes, which are in some sense always our model code. Random codes are by no means locally testable, and coming from this direction of coding theory, you would never come up with the idea of locally testable codes because you don't see them existing anywhere. However, through the construction of PCPs and through these ideas from interactive proofs, you can construct locally testable codes. So these are objects that are very special and are not random. And indeed, the LTCs were constructed inside the proofs of the PCP theorem. And we know of many different locally testable codes that are kind of derived from PCPs, but all of them are not good codes in the sense of information theory. In information theory, we like error correcting code to have as little overhead as possible, so that, another way to say it is that the rate of the code needs to be positive. You can't have rate going to 0, which means that the number of code words is tiny. So all the previously known LTCs had very small rate, but this recent work started out from this notion of the high-dimensional expanders that have local to global features akin to PCPs. And from them, we managed to construct LTCs with a good rate. Okay, so these are our main results I wanted to talk to you about. It's work with Evra, Lubotsky, Livne, and Moses, very recent. And what we show is that for every rate, there exists a constant delta, which will be the distance, and constant number of queries, and a family of error-correcting codes that have rate above r and distance above delta, and it will be locally testable with q queries, a constant. So you have LTCs for every rate all the way up to 1, which is a priori, I mean, for many years, people tried to prove lower bounds that these things don't exist, and myself is included. But in the end, they do exist. And in fact, they can be even more powerful than we thought. And amazingly, I want to point this out, in parallel, there are two scientists, Panteleev and Kalachev, that achieved almost an identical construction. And they also constructed an additional object from this called the quantum LDPC code, without saying what it is. So I'm just pointing it out in case someone is interested to look. Okay, so now I want to tell you in the remaining, I guess, 10, 12 minutes that I have, a little bit about our construction of these locally testable codes. So I'll start by talking about expander codes. These are beautiful codes constructed by Sipser and Spielman 25 years ago. And what they do is they take one specific base code, C0, on D bits, when D is a constant, like 10, and an infinite family of D regular expander graphs. So kind of at the heart of these codes are these expander graphs. These are graphs that on one hand, every vertex only sees D neighbors, very small, but the entire graph is very robust and very highly connected. So Sipser and Spielman take an expander graph in a base code and construct from it a code, an error correcting code that not only does it have a good rate and good distance, it's also decodable in linear time. And the way they did it is that they defined the code using the two components. They said, who are the code words in my new code? They're all the functions on the edges of the graph, so that locally around the vertex, every vertex looks at the bits around it, and these bits need to belong to the base code. Why is this a good idea? Well, let's see that this code has good distance. Suppose I have two words that are different and are inside this code. Well, they must differ on some point, right? So suppose there is some edge where these two code words are different. Now look at the vertex touching this edge. This vertex sees some small local view for the first word and some other local view for the second word, because they are different. But because the local view of this vertex belongs to the base code C0, it needs to see two different C0 code words. So there must be many other points of disagreement. So from one edge of disagreement, now I see a few edges of disagreement. And now I move to the vertices and I see even more edges of disagreement, and so on and so on. And here, the expansion comes to play. The fact that this graph is an expansion means that the amount of disagreement propagates further and further out, and you end up showing that two different code words must differ in a linear number of bits. So that's how expansion comes into play here. What is the new construction? We imitate the Sipser-Spielman construction, but we raise everything one dimension above. So instead of an expander, we have a high-dimensional expander. So it's not just an expander graph, it's now an expander graph that also has a second dimension. What's a second dimension for a graph? Well, generally, it's like in geometry. When you have points and lines, these are one-dimensional objects. And two-dimensional objects, you need to also look at maybe planes or other two-dimensional objects. So for us, it will be squares. So we'll have vertices, edges, and also squares. And as our base code, we'll have a code that itself is a small locally testable code. And together, combining these two things, we will get our family of locally testable codes. So we will see this. Really, I won't really have time to describe everything. I just want to give you a sense of the high-dimensional expander that we construct that will underlie this code. Okay, so I want to show you how we construct this graph that also has squares, and in a way that is in a high-dimensional expander. So we start, our object will be called the left-right Cayley complex. So we start with a group G, and we take a small set of elements in G, A, which is closed under inverses. And then it is a well-known object that we can construct the Cayley graph of G with A. It's a graph whose vertices are elements of G, and edges connect G to A times G. Now, I can do it now twice. I take two sets of elements, one A and one B, again closed under inverses. But now I connect G to AG for every element in A, but I also connect G to G times B, where for the B elements, I multiply on the right, and for the A elements, I multiply on the left. So really, I have here two Cayley graphs, one with respect to left multiplication, and one with respect to right multiplication. So I think of it as if the edges, there are some edges that are blue edges for left, and some edges that are red edges for right. And the interesting thing is that this gives me squares in the graph. So for every triple A, G, and B, we have a rooted square that goes from G to AG and then to AGB, and also from G to GB and then to AGB. So we close a square. And every square can have 4 different roots, and we identify them all to have squares that have no roots. So these 4 different ways to view this square, we identify them as one single square. And then this square contains the edges, as you can see in the picture, and the vertices. Okay, so formally this object, this left-right Cayley complex, is a square complex. It has vertices G, edges the EA and the EB, going from G to AG or from G to G times B. And it has these squares that we discussed. And we're going to say that this thing is an expander if each one of the Cayley graphs comprising it are themselves expanders. I didn't say exactly what an expander is, so just intuitively think of something that is very robustly connected. You cannot disconnect it without kind of erasing many edges. Okay, so I want to now look a little bit at the local structure. How does the local neighborhood look in this square complex? Because it's kind of nice. If I have an edge connecting G to AG, who are the squares that touch this edge? Well, it turns out that for every element B, I have a square GAG, and then it goes to G times B1, AGB1, and back to AG. So for every element in B, I have a different square containing the edge GAG. So this edge is really like the spine of a book, and different squares are like the pages of this book. And similarly, if I have an edge from G to GB, then the elements of A are kind of biject to the different squares containing this edge. And again, you can think of this edge as a spine of a book, and all these squares are like pages in the book. Now, the interesting thing about this complex is that you have your spines and books, but each page has 4 different sides, and you can really turn the book on all of them, right? So the picture is more complicated. It looks something like this. And if you're wondering, I didn't just copy this figure off of Google. Google doesn't have such things. As far as I know, it's the graphic designers of the Simons Institute that drew this for us. So the picture is even more kind of interesting when you look at all the squares that touch a vertex. I won't go into it, but you can really see that there is like a tensor format. Locally, the squares containing G, they look like a product. They have a product structure. And that's going to be very important for defining the code. So far, I just defined for you this object, the left-right Cayley complex. It's a new object. It's very, very simple, but it has these properties of high-dimensional expansion, and they're very useful for us. I see that I don't have much time, so just show you that to define the code, we do something very similar to Sipser and Spielman, but now we put the bits on the squares, not on the edges. And every edge requires that the squares around it, the bits that they see, belong to some base code. So I don't want to go into the details because I'm kind of running out of time, but you can see that the definition of the code, it takes one line, right? Given the left-right complex and given base codes CA and CB, which you can take to be the same C0, the code is just all the functions of this on the squares that satisfy some local conditions around the edges. So I'm kind of very, very proud that this is a very simple definition of the code. And kind of the key is that this code, you can prove for it that it has high rate, as close to 1 as you want. That's actually easy to prove. You can prove that it has constant distance. This follows from the expansion. It's also easy to prove. And you can prove that it's locally testable. That's less easy to prove, but it follows from the fact that locally around the vertex, this product structure means that we're looking at a tensor code, and for that we already know some local testability, and then the expansion gives the full result. Okay, I realize that I'm just flashing some slides at you, so it's just to get a feel. Okay, so that's all I wanted to say about this new construction of a locally testable code, as opposed to previous constructions that all came from probabilistically checkable proofs, that you took this construction of a PCP and you stripped it down, you got an LTC. Here, we use high-dimensional expansion, which is a completely different direction, to construct a locally testable code. So what is the naturally open question? Okay, we have a locally testable code. Can we get PCPs out of this thing? And the reason I'm interested is that we have many open questions about PCPs, certain parameters, various questions, and it would be really interesting to get PCPs through this direction. And also, just getting a very different way to get PCPs sounds like it will teach us something new. So with this, I think I'll almost end. So to summarize, I talked a little bit about P and NP and how PCP fits into the picture. PCPs are kind of have been running strong for the past 30 years, and there's a lot of work on hardness of approximation. And in the end, I discussed some recent work with my colleagues showing that locally testable codes can be constructed in a very different path. So thank you for your attention, and I really wish good luck to all of you. I understand that some students are now celebrating their graduation, so I wish you all the best, and thanks again.
Yeah, thank you very much, Irit, for this wonderful lecture. I know from my own experience that whenever you have to give such a talk online, it's difficult in the sense that you don't really connect to the audience. But I can assure you that when I look around here, I see many excited eyes. So people are really fascinated by what you have, by what you told us. So thank you very much for that. That was wonderful. So now there is time for questions, and also those that are joining online can ask questions. Just type your question into the chat, and then this can be read out here. But I see there's a question in the audience here, so we have a microphone over there.
Thank you for the talk. You increased the dimension of the graph, or like you moved from a graph to like some higher dimensional object. Is it possible to increase the dimension even more? And would that even be useful for anything?
Okay, lovely question. Thank you very much for the question. So there are high dimensional expanders of all dimensions, but we don't know of a way to increase our construction further without taking the groups to be a billion, and then the thing won't be an expander anymore. And this is actually important, for example, for the applications to quantum LTCs. So that's an object that combines both the local testability and the quantum LDPC. So this is a question that's of a lot of interest. I don't know how to increase the dimension here, but in more general, we do know constructions of simplicial complexes of any dimension that are sparse and expanders, and we also know constructions of square complexes. In higher dimension, they're called cubical complexes that are very, very good expanders. The problem with those constructions is that we don't know how to make a code on them, and okay, it's a bit, I cannot explain what is missing, but there is some commutativity that is lacking, and we're still kind of confused by that.
Kurt has a question, please.
Very nice talk. I have a question with respect to the beginning. So you said we have this formula phi, we construct the psi, which is then very easy to check whether it's satisfiable or not. Or we can. So who constructs the psi from the phi? Do I? Then I would really have to account for the combined work of constructing the psi and then checking. Or does the other person construct the psi from the phi? And then how do I know that he didn't cheat me when he constructed the psi from the phi?
Okay, thank you. Excellent question. Okay, so there are two people involved here, right? There is the verifier that wants to know if phi is satisfiable or not. Maybe for the benefit of the other, is this it? Here. So there is the phi that you want to know if it's satisfiable or not. And then there's a PCP algorithm that constructs psi. And then the other person is the prover who gives you a satisfying assignment. First, he wanted to give you a satisfying assignment for phi, but if he gave you that, you don't know how to check it. Instead, he can give you a satisfying assignment for psi. So really, the work that you do is a lot of work. You need to read phi, compile it, construct psi, all on your own, but you do all this without reading a single bit of proof. And then we only measure how many bits of proof are you reading. So now the prover gives you a proof for psi, and you only read a small number of bits. So that's kind of the power of PCPs. You are right to feel that you did need to work a lot because you needed to invest polynomial time to read all of the formula phi and to compile psi. But I forgot to mention, and your question actually gives me an opportunity, PCPs have been tremendously useful for hardness of approximation, but in recent years they have been useful also in industry. So a lot of cloud computing, for example, needs this asymmetry between, it's like a verifier and prover. You, with your cell phone, have small computational power, and the cloud, with all its servers, has a lot of computational power. So you want the cloud to do some very complicated calculation for you, and you want to check that he's not cheating you. So people use PCP protocols for that, and they need to overcome exactly the kind of question that you raise, and they do it using some extra cryptographic means. So there are ways to solve this.
There is next a question from the online audience that Ariane will read to us, as far as I understand.
Yes. First, thank you very much for the talk. And then there's a question from John Sullivan, who wants to know, for the left-right Cayley complex, is it important that A and B be different sets of generators?
Okay, thank you for the question. The short answer is no, they can be the same. If you want to have a nice regularity property that no squares kind of squish on themselves, and you want the local picture from every vertex to be completely a product with no parallel edges, then you might want A and B to be not only different, but maybe A will be, say, generators of order 2, and B will be generators of odd order. And so if you do it this way, they are never going to be conjugates of each other, and that promises that no squares will collapse. But if you don't care about that, and for the proof you don't need that at all, you can just take A to B equal to B.
There is a question.
Yeah, so hello. The PCP theorem helped to understand the relation between P and NP. Is there something for co-NP or higher levels in the polynomial hierarchy?
Okay. So we do know theorems like IP equals P space. So for higher levels of the hierarchy, we do know of ways to connect between, say, P space and some kind of interactive proof. But in terms of like robustness and PCP type of transformations, I don't know too much about this. So maybe it's a good place to start thinking.
Are there further questions? Either from here or from the online audience? That's not the case. Then thank you very much again, Irit, for this really beautiful, wonderful talk. And of course, we wish you all the best and very much hope to see you in Berlin at some point. As I understand, you have not visited Berlin so far, so we very much hope that you will do so in the future. We can welcome you here in person. So thank you very much.
Thank you.